Okay, so here we also introduce a thing called magnetic field lines. So actually we have the similar field lines for the electric field. So actually the concept are the same. So you can see they should follow two rules. The first one, the direction of the tangent to the magnetic field line at any point gives the direction to the B of the B field at that point, and then the spacing of the line represents the magnitude of B. Okay, the magnetic field, or I should say the B field, is stronger where the lines are closer together and conversely. Okay, so we just replace E field by B field and all the things to be the same thing. Okay, and as you can see here, this is a magnetic bar, so actually it is like a magnetic dipole. Magnetic dipole. So it will generate some B field like this. And if you remember, if you have an electric dipole, okay, it will generate similar pattern. But for E field, okay, the E field can be something like this. Okay, like an apple, something like this. Okay, but this is for the electric dipole. Electric dipole. Okay, something like this. And so this one try to demonstrate. So in between there's a magnetic bar, and then it try to place some iron fillings. Okay, 就是这个铁的屑了，铁的屑。Then this iron fillings, okay, will follow the B field line. Okay, somehow like that. Okay, somehow like that. And so the iron fillings at its end we view the magnetic field lines. Okay. Okay, so similar to the E field line, so nothing special. Okay, so actually here you need to mention that the point for the two poles. Okay, so this is the highlight. So it says opposite magnetic poles attract each other and line magnetic poles repel each other. Okay, so this is still nothing special. So if you have another magnetic bar, so North Pole, South Pole, so North Pole and South Pole will attract each other, and North Pole and North Pole will repel each other. So I think a primer student should also know this. And one more thing is that we cannot have magnetic monopole. But for electric dipole, you can actually separate the charge into a single positive charge or single negative charge. But for magnetic dipole, you cannot actually separate the dipole into a monopole. Okay, suppose if you try to cut the magnetic bar into two pieces, and then even a primary student will know it will form a new North Pole and South Pole, North Pole and South Pole, something like this. Okay, you cannot really create a magnetic monopole. So this is very important. This is very important. This is related to the form of the Maxwell equation. So actually in chapter 23, we have learned the Gauss law. So for the Gauss law, it is something like this. Okay, integration of E dot dA, and then multiplied by epsilon naught equals Q enclosed, if you still remember. And actually so this is the Gauss law for electric field, but the Gauss law for B field, of course, we will learn it in chapter 32. But actually, it is actually related to this point. Magnetic monopole does not exist. Okay, so the Gauss law for B field will be something like this. Because we don't have monopole. So no matter how you enclose the magnet bar, so the total magnetic element will be zero. The positive and negative will always cancel each other. So it says, so if you have interest about that, you can check it out on the Wikipedia. It says the magnetism in bar magnets, electric magnets, is not caused by magnetic monopoles. Okay. For the electric dipole, it actually formed by positive and negative charge. Actually, you can separate it, separate it into positive charge or negative charge. But yeah, here you cannot have a magnetic monopole. And indeed, there is no known experiment or experimental observation evidence that magnetic monopole exists. OK， 所以刚才就说就是这个没有这个磁单极的话磁单极是不存在的嘛，磁单极，那它就会影响到这个Gauss law 的 B field 形态的它右手边只能为零，因为你无论怎么框住那个磁铁它都是 dipole 它都是 dipole， 就是正跟负它都会抵消掉，所以它永远都是零在右手边。那当然有些理论物理学家他就是假设这个存在的话 ，Maxwell equation 会变成怎么样呢？它就会多一些项出来，那就是另外一个故事。但是这个至少不存在我们所存在这个宇宙里面嘛。Okay, so here we have a sample problem. So it says a uniform magnetic field with magnitude 1.2 millitesla. Okay, so I forgot to introduce the SI unit for the B field. Okay, maybe just go back a bit. Okay, so here, I forgot to highlight it. Okay, so actually the SI unit for the B field is actually Tesla. Okay, so Tesla. So of course the car brand Tesla is named after him. Actually Tesla invented the AC electric, which is a competitor with Edison. Okay. 就是那个特斯拉是当时是跟那个爱迪生是那个死对头是那个死对头那爱迪生是站在那个直流电的那一派那特斯拉的话是交流电的他们就是死对头了，反正就是。Okay, so actually with a magnitude 1.2 millitesla, okay, and direct vertically upwards throughout the volume of a laboratory chamber. Okay, so a proton with kinetic energy 5.3 mega eV. Okay, if you still remember, this is a unit for the energy. It is not an SI unit. The SI unit for energy is joule. Yeah, so if you still remember, we need to have some conversion between EV and joule. Okay, multiply or divide by 1.6 times 10 to minus 19. Okay, enter the chamber, moving horizontally from the south to north. What magnetic deflecting force, which means the Lorentz force, acts on the proton as it enters the chamber? The proton mass is this one, and neglect the Earth's magnetic field. Okay, so first of all, we know the kinetic energy. We know the kinetic energy of the proton, so we may be able to calculate its velocity. Okay, because if we need to calculate the Lorentz force, we should know its velocity. Okay, so V equals 2k over m, and then take the square root of the whole term. Okay, if you don't forget this one, it should be coming from k, the kinetic energy is half of mv squared. Half of mv squared is the kinetic energy. Okay, so actually we can just plug in the numbers. Okay, so 2 times k is 5 times 3 times 10 to the 6th power, 5.3 mega. Okay, but we need to convert it back to joule, so that it is SI unit. So we need to multiply it by 1.6 times 10 to minus 19, and then divided by 1.67 times 10 to negative 27. And then we take the square root of the whole term. So it becomes 3.2 times 10 to the 7 millisecond. Okay, so now we know the velocity. We also know the B field. Then we can calculate the FB equals Q VB sine of phi. Okay, so here we know that the B field is actually pointing out of the page. Okay, so we use a green dot to represent that the field is pointing out of the page. Out of the page. Okay, if it is using a cross, okay, something like this, then it means the field is pointing into the page. Okay, into the page. So this is just a notation. Okay, so a cross, like you can see the tail of an arrow. So it's like a cross, and then and if you see the front of an arrow, so it's like a dot. Okay, the idea is like that. Okay, so B field is pointing out of the page, and then the V is moving upward. Okay, moving upward. So V and B are actually perpendicular to each other. So so actually we have Q to be 1.6 times 10 to minus 19. It is a proton, so with a charge of positive E. And then V is what we have calculated just now, 3.2 times 10 to the 7th power, and then times sine of 90 degrees, okay, which is 1. Okay, sorry, I forgot the B. I forgot B is 1.2 times 10 to the negative 3 power Tesla, and then times sine of 90 degrees. Okay, so the force will be 6.1 times 10 to negative 15 Newton. Okay, which is quite small. Which is quite small. Okay. So it's nothing special. We just find the velocity from the kinetic energy, and then we just plug in all the number in this Lorentz force. And then it asks you how large is the acceleration of the proton. So according to Newton's second law of motion, F equals ma. So A equals Fb over m. So it is actually 6.1 times 10 to negative 15 over 1.67 times 10 to negative 27. Okay, so actually the force is very small, but the mass is even smaller. So the acceleration is really high. Okay, 3.7 times 10 to the 12th power meter per second squared, which is a very high acceleration. Okay, so it is this sample problem is pretty easy. So we move to next part. So here we talk about the cross field, and then the subtitle is discovery of the electrons. Okay, discovery of the electrons. Okay, so okay, so let us. So there are too many texts. Let's look at the figures directly. Okay, so on the left-hand side, we can see this is a battery. So this battery will provide a potential difference between, for example, this node A and node B. Okay, there will be a potential difference provided by this battery. And then we have another battery connecting this side and also this side and also the screen. Okay, so there will be a potential difference between this part and this part. Okay, so you can imagine there will be a E field pointing to the left side. Yeah, there will be a potential. Yeah, so it will actually, so here for this part it will actually generate some free electron at this part, and then with this potential difference, the electron will accelerate will accelerate from this part up to the screen. Okay, so there will be an initial velocity. There will be an initial velocity going through the screen. If it is not exactly going through the screen, then it will be blocked, and then it will be absorbed somehow like that, or reflect. Okay, so some of the electron may be lucky enough to go through this hole and then going to the right side. So in that case, here we try to generate so-called the cross field is at this part. The cross field is at this part, which means that we have E field and B field perpendicular to each other. So we call it cross field. Okay, 就是交叉的场. Okay, cross field. Okay, so here it says. Here we have a parallel plate, okay, so and then providing some potential difference, so there will be E field pointing downward. And then in some sense we can also generate some B field going into the page. Okay, so here we have some green cross to represent that the B field is actually pointing into the page. Okay, so this B field and E field are perpendicular to each other. Okay, so in such a way, the electron is going to the right side, okay, starting from here with a uniform speed. But after it enters this cross field, there will be some difference, okay. So so it says if a charge moves through a region containing both E field and magnetic field, or I should say B field, it can be affected by both an electric force and magnetic force. When the two fields are perpendicular to each other, they are said to be cross field. Okay, just as what I mentioned, if the forces are in opposite direction, one of the particular speed will result in no reflection of the particle. Okay, so actually we can simply consider. Suppose we have a E field. We have an E field pointing downward, and it is an electron, which is a negative charge. So there will be Fe. Okay, suppose the electron is at this part. Okay, so there will be Fe. Fe. Fe is pointing upward, right? Fe is actually equals to E times capital E. Okay, E is the elementary charge, and then capital E is the E field. Okay, and then for the B field, okay, let's consider the direction. V is pointing to the right side. Okay, so we use our hand pointing to the right side, and then the B field pointing into the page. So we cross into the page. Our thumb is pointing upward. So this is the direction of V cross B, and this is a negative charge. So FB should be pointing downward. Okay, so we have FB. FB should be pointing downward. And in this case, FB should be equal to QVB. Q is actually E, and then we have V, and then we have B, and then sine of 90 degree will be 1. Okay, V and B are also perpendicular to each other, so sine of 90 degrees is 1. So in such a way, it says in a particular condition, we can have Fe equals Fb. Okay, which means E times capital E equals E times V times B. So in this case, we can actually cancel E and E, so the elementary charge doesn't matter. Okay, so which means that if V equals E over B, okay, if V equals E over B, then there will be no force acting on this electron. Okay, so which means that if we just set E and B arbitrarily, okay, maybe Fe to be stronger, or maybe Fe to be weaker. So if Fe is stronger, then the charge may be somehow like this, going slightly to the top. Or if Fe is weaker, then the electron may be going downward. Okay, slightly downward. Okay, so if we may be able to tune the intensity of the E field or the B field such that we can tune the ratio of E over B, then if E over B is actually equals to V, then it actually go in the middle path. Okay, going to this part. Okay, so next we also talk about a very important experiment called the Hall effect or Hall experiment. Okay, so this actually tells you the moving particle in the conductor should be negative charge rather than positive charge. Okay, so here it says, as we just discussed, a beam of electron in vacuum can be deflected by B field. Okay, can the drifting conduction electron in a copper wire also be deflected by a magnetic field? Of course, the answer is yes. And in 1879, okay, Hall, a 24-year-old graduate student at Johns Hopkins University, showed that they can. Okay, this Hall effect allows us to find out whether the charge carrier in conductor are positively or negatively charged. And of course, the conclusion is that the charge carrier must be negatively charged, but not positively charged. Okay, beyond that, we can measure the number of such carrier per unit volume of a conductor. Okay, so it's some sort of hardcore physics stuff. Okay, so here, so here we try to assume some variable first. So we have a Cooper strip with width d. Okay, so here you can see this is d. Okay, this is the width d. And then carrying a current I. Okay, so we have current I going downward. Okay, and then okay, and then with a drift speed Vd, Vd. Okay, so here we first assume that the charge is negative first, and then go through the whole discussion. And after finishing this, I try to assume the charge is positive, and then to see how it will be confection. Okay， 就是我们就先假设说它是我知道答案就是电子就是负的，然后去完成这个讨论。那结束之后，我再假设这个 charge 是正电荷的，那然后看有什么矛盾的。Okay, so as the time goes on, electron move to the right, move piling up on the right edge of the strip. Okay, so let us see what it really happens here. So in the figure, we assume that there is a current going downward. So if the charge is actually negative, which means that the drift velocity should be pointing upward. And here we try to generate an external B field. Okay, so this is an external B field. External B field, okay, which is pointing into the page. So in such a way, V and B are perpendicular to each other. Okay, so here, as we can see, this is a charge, moving charge. Okay, in the uniform B field, so there will be Lorentz force acting on this electron. So in such a way, we first need to determine the direction of force. So V is pointing upward, and then the B is pointing into the page. So we cross it, and then V cross B is pointing to the left side. And then the charge is negative, so the FB should be pointing to the right side as this one. Oh, sorry. As this one, okay, FB is pointing to the right side. Okay, so which means that there will be force acting on the electron in such a way there will be more and more electron accumulate on the right side. But the wire should be electrically neutral. So which means that the total charge should be 0. So which means that if there are negative charge accumulating on the right side, there should be some positive charge accumulating on the left side so that the charge can be cancelled out. Okay. So which means that if we have accumulate charge on the left, accumulate positive charge on the left side and accumulate negative charge on the right side, these two accumulate charge group will generate E field. Okay, will generate an E field. Okay, so this is a dynamic reaction. Okay, so it's you need to go through it step by step. So here, as much as we have accumulate charge, it will generate E field pointing to the right side from the positive charge to the negative charge. In such a way, this is a negative charge. So in such a way, the Fe or the Coulomb's force should be pointing to the left side. Fe is pointing to the left side. Okay, so here the idea is that if Fe at the beginning should be weak, because at the beginning there should be no charge accumulate. So there will be a larger Fb and a weaker Fe. Okay, so that more and more charge will, more and more negative charge or more and more electron will be accumulated on the right side to make this E field stronger and stronger. Okay, if this E field is stronger and stronger, then which means that this Fe will be also stronger and stronger. So until Fe is as large as Fb, then there will be no force acting on this on the electron anymore. Then in this situation, there will not be further electron accumulating on the right side, become an equilibrium point， 就是到达一个平衡，就是一开始的话就是一开始什么都没有，那它在动，它在磁场里面动，它在 B field 里面动，它就会有一个 Fb， 这个 Lorentz force 向右把那个电子推到右手边，那同样的就会有相同分量的正电荷在左边累积啊。那一开始的话 Fe 很弱，Fb 很强，所以就会越来越多电子在右手边去累积，让这个E field 越来越强。那这个 E field 越来越强的话，这个 Fe 也会越来越强，强到的话就是 Fe 跟 Fb 相等，就不会再有尽力让电子往右手边累积，那就到达一个平衡的状态。OK， 所以就是大概就是这样。那这个就叫做 Hall effect。OK， so when a uniform B field is applied to the conducting strip carrying current I, the field perpendicular to the direction of the current, Hall effect potential difference is set up. Okay, so we will have a Hall effect potential difference. So because there is charge accumulated on the left and right side, so in such a way we can, if we use a voltmeter to measure the left side and the right side, there will be a potential difference. So this one is called the Hall effect potential difference. Okay, so here we have some formula to derive. So this one V equals ED. So we just assume the E field is uniform inside the wire. And then if we have a Fe, okay, this one is due to Fe equals Fb, okay, to reach the equilibrium situation. Okay, so we have QE equals QVD times B. Okay, and Q can be cancelled. Q and Q can be cancelled. So it also becomes E over B equals VD. And also we have VD equals J over NE, just as what we derived before in chapter 26. And then J equals, so here we have J equals I over A. Okay, so it becomes I over NE times capital A. Then we can, then we can do some cancellation. So the idea here is like, we have so from this one we have n equals EA VD over I. And actually, EVD equals E over B, so here we have a EA E over B. Sorry, it should be the reciprocal. It should be the reciprocal. Okay, n is in the denominator, so it should be like I over VD times E times A. Okay, something like this. Okay, and then VD equals E over B. Okay, so here we should have EBI and then E times A. Okay, so yeah, here we more or less have this BI and also we have this E. Okay, so the remaining things is whether EA is equal to VL. EA is equal to VL. So actually it should be correct. Okay, L is actually A over D. L is actually A over D. A is the cross-section area. A is the cross-section area here. And then D, D. Okay, A is the cross-section area. Okay, this part is the cross-section area. And then it should be A equals to L times D. L is the length of this part, and then D is the width. Okay, so we have A equals LD. Okay, so in this case we have BI times E times LD times small e. Okay, and then we have this E times D to be V. E times D to be V. So we have V. L, E, and then we have a BI. Okay, so finally we can actually derive this 2812. So this one tells us that we can actually know the charge density inside the conductor. Okay, so this B field is what we generate externally. And then the I is the current, so it is easy to measure. And then the V, this V is actually the Hall effect potential between the left side and the right side. And then the L is the length of the wire, and then the E is the elementary charge. So all this variable is possible to be measured. Okay, so we may be able to use all these variables to calculate the charge density. And here we have a simpler, easier formula. So for us to use for the Hall effect. Okay, so it says when the conductor moves through a uniform B field at speed v, the Hall effect potential difference V across it is V equals V times B times D. Okay. So it is very trivial because we have a V equals E times D, and then according to this one, E equals VD times B. So actually we have V, you can say it is VD times B times D. Okay, so whether you write as a VD or V is actually the same thing. So this Hall effect potential is equals to this is the drift velocity times the B field times the width of the wire. Okay, so next will be a sample problem. So before going to that part, let me finish this part. Let me assume the moving charge to be positive, And then let us find the contradiction. Okay, so here, if we assume that it is a positive charge moving downward, okay, just follow the direction of the current. Okay, suppose the current is moving downward. If the charge is positive, then VD should also be pointing downward. So in this case, V cross B, V is pointing downward, B is pointing into the page. So in this case, V cross B is pointing to the right side. V cross B is pointing to the right side. And V cross B is pointing to pointing to the right side. And this is a positive charge, so which means that FB is also pointing to the right side. In such a way, there will be positive charge accumulate on the right side. But this contradicts with the measurement. During the measurement, we can really confirm that this side will have a higher potential. But if the moving charge is positive, it will lead to positive charge accumulate on the right side. And in such a way, negative charge will be accumulated on the left side. So that in this case, there will be the opposite polarity of the potential difference across the strip. So so this is not okay to have a moving charge to be positive. Okay, so far any questions? Okay, so let us finish this sample problem and then we can have a break. So it says a solid metal cube, OK， 就是一个固体的铁的方块了，就是立方体。At edge length, d equals 1.5 centimeter for each size, moving in the positive y direction. Okay, moving in the positive y direction at a constant velocity of magnitude 4 meters per second. The cube moves through a uniform B field of a magnitude 0.05 Tesla in the positive z direction, which cube face is at lower electric potential and which is at higher electric potential because of the motion through the field. Okay, so here we have a B field pointing to the positive z direction, and then this V is pointing to the positive y direction. Okay, so first of all, we can determine what is the direction of FB. What is the direction of FB? Okay, so here V cross B, V is pointing upward, B is pointing to the Z direction. Okay, Y cross Z will be positive X. Okay, so this will be V cross B, V cross B. Okay, so yeah, so actually the moving charge is actually electron, so it's a negative charge, which means that FB is pointing to the right side. So in such a way, we will have negative charge accumulate on the left side and positive charge accumulate on the left side. So negative charges on the left side. On the left side, negative charge, or it means that the left face has a lower potential, lower potential. Okay, 比较低的电位。Okay. Okay, so for part B, what is the potential difference between the phase of higher and lower electric potential? So it will be very trivial. So using this, V equals small v times B times D. Okay, as we know that the velocity is 4 meters per second, so 4 times the B field is 0.05 Tesla, okay, and then times this D is 1.5 centimeter, which is 0.015. Okay, so the answer will be 3 millivolts, okay, which is not a large potential difference. Yeah, but it is actually measurable using some using a voltmeter.